Okay, good afternoon, all of you. In last session, we started commutation methods. And before going to commutation, we derived the expression for capacitor current, capacitor voltage, and voltage across inductor by taking a simple LC circuit. This one is the switch, and this one is the inductor, and this one is the capacitor, and this one is DC voltage. So when the switch is closed, current starts flowing in the circuit, and that current is I of t, and we derive the formula for current I of t. Current I of t equal to square root of C by L Vs minus Vc naught sin omega t. Here omega means angular resonance frequency. Omega equal to square root of 1 by Lc. Next, voltage across capacitor. Vc of t equal to Vs into this one is Vs 1 minus cos omega t plus Vc naught cos omega t. Here Vc naught means initial voltage across capacitor. Initial voltage across capacitor is Vc naught. And voltage across inductor VL of t equal to Vs minus Vc naught cos omega t. These expressions are already derived in the last class. And suppose if we consider initial voltage across the capacitor is 0, it means Vc naught equal to 0. Then I of t equal to square root of C by L Vs sin omega t and Vc of t equal to Vs 1 minus cos omega t and VL of t equal to Vs cos omega t. Next, we draw the waveforms for these conditions. For these equations, we draw the waveform for voltage and current. This one is I of t. This one is Vc of t. This one is VL of t. So if you observe this equation, I of t equal to square root of C by L Vs. Here square root of C by L is Vs is the peak value, peak current or maximum current. This one is Im. This one is Im sin omega t. So this one is the graph 0 to pi. And after pi, we neglect the current. We neglect negative upcycle because here this switch means power semiconductor devices like diodes, SCRs. So all these devices are unidirectional devices. So unidirectional devices does not allow bidirectional flow of current. So it blocks the negative upcycle. So here our aim is to turn off SCR. To turn off SCR, our requirement is we can turn off SCR by two methods. So if you make the reverse bias, if you make it reverse bias, then it will be in a reverse blocking mode. So SCR will be in off state. This is one of the method. So by applying negative voltage across SCR, we can turn off SCR. This is one of turn off method. Next method is this one SCR, and if the switch is conducting and this one is anode current, Suppose the maximum amount of current flowing in this SCR is 5 amperes. Suppose if you supply reverse current in reverse direction, if you supply current in reverse direction, suppose if you supply 5 amperes current, 5 minus 5 amperes, so net current equal to 0, which is less than holding current. Or if you assume holding current is 2 amperes, holding current is 2 amperes. If you assume holding current is 2 amperes, if we supply 3 amperes or 4 amperes, if the reverse current is 4 amperes, then the net current is 5 minus 4. 2 ampere, 1, 5 minus 4, 1, which is less than holding current 2 amperes. So by this method also we can turn off SCR. So these are the available techniques to turn off SCR. One method is by maintaining reverse voltage across SCR, or another method is by supplying reverse current in the SCR. By these two methods, we can turn off SCRs. Suppose if the reverse current is decreases means suppose initially we supply 1 ampere, then 5 minus 1, 4. Then anode current, it is the anode current. It is the anode current. At this point, if you supply 1 ampere current, the magnitude of anode current decreases like this. After certain time, if you supply reverse current 5, then the resultant current decreases like this. Again, if you increase to 3, 5 minus 3, the net current will reduces like this. And with increasing reverse current, anode current becomes 0 like this, and we can turn off SCRs. So from 0 to pi, after pi, current will be negative, and in this time period at omega t equal to pi, current becomes 0. So thyristor will be turned off, and there is no flow of current after pi. After pi, there is no flow of current. So coming to VC of t, if you substitute omega t equal to 0 degrees in this equation, omega t equal to 0, then cos 0 value 1, 1 minus 1, 0. If you substitute omega t equal to 90 degrees, cos 90 value 0. So the final remaining value is Vs. So at this time, so this one is Vs. Again, after omega t equal to pi, after omega t equal to pi, cos pi value minus 1. So 1 minus of minus plus 2 Vs. So this one is the plus Tvs, which is the voltage across capacitor. So after omega t equal to pi, there is no flow of current. So capacitor remains constant and capacitor does not charge. So this voltage remains constant in the capacitor. This voltage remains constant because after omega t equal to pi, this switch is open. After omega equal to pi, this switch is open. Once the switch is open, at omega t equal to pi, capacitor voltage is 2 Vs. So there is no closed path to discharge the capacitor voltage. So capacitor voltage is maintained 2 Vs until closing switch. So this one is the constant voltage which is maintained until turn on the device. So next coming to voltage across inductor. This one is Vs cos omega t. At omega t equal to it will be omega t equal to 0, it has maximum value. This one is Vs. At omega t equal to 0 means cos 0, 1. So it is Vs. At 90 degrees, 0. Next at 180 degrees, minus Vs. So this is the voltage across inductor. Next, after pi, the formula for voltage across the inductor is VL equal to L into di by dt. So if the current is 0, then there is no voltage across inductor. Voltage is also 0. So after omega equal to pi, voltage across inductor equal to 0. These are the waveforms at different time intervals for simple LC circuit. So same concept is applied in class B commutation. And the other name of class B commutation is current commutation or resonant pulse commutation. These are the other names of class B commutation. Class B commutation is also known as current commutation or resonance pulse commutation. Coming to circuit, this one is our main SCR. This one is SCR, and this one is the supply voltage VS, and this one is the load. Here, for our convenience, we assume load current I naught is constant. So for to get constant current, we need to take highly inductive load. So the property of inductor is it opposes sudden change in voltage. So if you take highly inductive, it opposes highly changes. So it reduces ripples. So the current becomes constant. So to make current constant, we need to take high inductance. So this is our assumption. So to turn off this SCR, we need to take commutating elements. So to turn off SCR, I take one more SCR. This one is SCR, not a diode. I take one more SCR and a diode and LC elements. This one is resistor, inductor and capacitor. So this is our main thyristor, and this one is auxiliary thyristor. Here, green elements, all the elements which are represented by green ink are commutating elements. Here, the main circuit elements are main thyristor and load source. These are the main red color elements are all elements are normal elements, and green elements are commutating elements which are used to turn off main thyristor TM. So initially assume both SCRs are in off state. If you assume both SCRs are off state, TM comma TA, both are in off state. Then the equivalent circuit is like this. This one is TM. So it acts as open circuit. This one also acts as open circuit. Here TA also acts as open circuit. And this one is the diode. And this one is the capacitor. And this one is inductor. And this one is load. And this one is source voltage Vs. So in this case, in this condition, Vs is the source voltage. The direction of current flow is like this. This is the direction of current. So diode is forward based, and in this time period, load current is supplied by voltage source through the commutating elements like C, L, and diode. So current flows in this path. and voltage up to this will be possible up to voltage across capacitor. If the voltage across the capacitor reaches its rating value, suppose if the rating of capacitor is Vs equal to Vc equal to Vs. Once the capacitor charges to supply voltage Vs, it acts as open circuit. It acts as open circuit once it reaches its rating value. Then the equivalent circuit is like this. Here capacitor also acts as open circuit. All elements are open. This one is the diode, and there is no flow of load current. So if you draw the waveforms, this one is for main thyristor gate pulse. This one is for main thyristor gate pulse. IMG, main thyristor gate pulse. IMG. This one is for TA means auxiliary thyristor, a commutating thyristor. TA thyristor gate pulse. Next one. This one is for load current I0. And this one is for main thyristor current IM. And this one for auxiliary thyristor current. And this one for capacitor current. Capacitor current IC. And this one is for capacitor voltage VC. So initially load current is supplied by up to this point. So take this line. So up to this point, the current to the load is supplied by capacitor. This one is load current. And in this time period, main thyristor is off state. So main thyristor current is 0. And also auxiliary thyristor also off state. So auxiliary thyristor is also auxiliary thyristor current is also 0. Next, capacitor current is increases. Assume this capacitor current is some minor, because in this condition, I0 is load current and which is passes through capacitor, inductor. All elements are connected in series. So capacitor current IC equal to I0. So this is the graph for I0. This one is I0 is constant, so similar to I0. Next, voltage across capacitor. Voltage across capacitor reaches to Vs. It reaches to Vs like this. So at this point, capacitor reaches maximum voltage. So I naught current becomes 0. I naught current becomes 0 like this. IM current is also 0. IA current is also 0. IC current becomes 0 because it acts as open circuit once the capacitor charges to rated voltage. So these are the currents. Now at this point, at this line, both SCRs are in off state. TM off and TA also off. PA comma main thyristor comma auxiliary thyristor both are in off state. At this condition, if we apply gate pulse to the main thyristor, this one is the gate pulse of main thyristor. The current in the main thyristor starts increasing. This one is the main thyristor starts increasing like this. So if you trigger this SCR, the circuit diagram will be like this. Here SCR is turned on. It acts as once the SCR is turned on, it acts as short circuit. This one is main thyristor. Auxiliary thyristor in this condition acts as open circuit because we cannot apply gate pulse to this circuit. And this one is capacitor. Capacitor also acts as open circuit because it charges to rated voltage. In this case, there is no flow of diode current because this one is open circuit, this one is open circuit, so this one is also open circuit. This one is load. So in this case, the direction of current is like this. This one is Vs and this one is I naught V naught. Here no need to draw output voltage because our aim is to turn off this SCR. So we need to draw main thyristor current, auxiliary thyristor current, and load current. No need to draw load voltage. In this time period, uh, this one is for auxiliary current. Auxiliary current is also 0. And the capacitor also under normal state. In this period, TM on. At this line, TM on, PA off. Main thyristor is on condition and auxiliary thyristor in off state. Now, here, this is the original diagram of class B computation. In class B computation, the main thyristor TM will be turned off. Main thyristor TM will be turned off by triggering TA. Once you trigger TA after certain time, TM will be turned off. This is the main process, main principle involved in this circuit. To turn off TM, you need to trigger TA. If you apply gate pulse to TA, TM will be turned off. So now apply gate signal to IA at this line. At this line, TM is off and TA is off after certain time. And voltage across capacitor is same voltage is maintained. This one is voltage across capacitor. At this point, if you apply gate pulse to auxiliary thyristor, this one is the gate pulse to auxiliary thyristor. So here also IA starts conduction. If you draw the circuit diagram, TA is on state. Sorry, it is TM is on state. This one is the source. This one is load. And in this time period, TA is also triggered. This one is TA. Once TA is triggered, these are the polarities while charging capacitor. This one is plus, this one is minus. Here is the inductor. Here no current flows in the diode on this path. So these are like open circuits. No current flows in this path. So I think all of you know the polarities of voltage and capacitor during charging and discharging. Suppose take a capacitor. If it is charging, the polarities across the plate is this one is positive and this one is negative, and the direction of current is from left plate to right plate. This is while charging. Next, discharging condition. In discharging condition, the polarities are same, but the direction of current is opposite. Coming to inductor. This one is the inductor. While charging, the direction of current is like this, and polarities are like this. While discharging,
Sir, both are inductors only, sir. రెండు ఇండక్టర్లేనా సార్?
Two are inductors, both are inductors. This is capacitor while charging. This is the capacitor while discharging. This one is inductor while charging. This one is inductor while discharging.
పైన రెండు కెపాసిటర్ అండ్ ఇండక్టరా సార్?
Two good capacitors we the condition of the capacitor while charging and the condition of the capacitor while discharging. This is discharging state. This one is charging state. Okay, same for inductor. This one is charging state and this one is discharging state. In discharging state of inductor, the polarities of inductor reverses like this, and the direction of current is same. And the direction of current is same as charging state. The direction of current is same as charging state in inductor, but the polarities reverses for discharging. If you take a capacitor, voltage polarities are same, but current direction changes for charging and discharging. For charging, it is from left to right, and for discharging, the direction of current is from negative to positive. Sorry, right to left, like. So any doubts about this topic? It means about charging and discharging. Any doubt about charging and discharging of inductor and capacitor? We need to know this topic because it is very useful for further classes. So all of you need to know this one.
మార్క్ అనేది కరెంట్ డైరెక్షన్ కదా సార్?
current direction. So this one is the direction of current while charging. So this one is the direction of current while discharging. So this is the discharging direction and this is charging direction.
Okay.
So this one is for inductor. The polarities is like this, plus, minus. And the polarities reverses, voltage polarities reverses during discharging of inductor. So it is minus and it is plus. But the current direction is same as charging direction. Is it clear? Any doubts? Okay. So if you take this capacitor, capacitor charges like this. Capacitor charges like this and polarities are like this, plus, minus. Next, in this case, capacitor discharges. So the direction of current is like this. This is the direction of current while discharging. So current flows like this. So this one is capacitor current, which is equal to auxiliary thyristor current. So here both currents are same. Here already we derived for LC resonance circuit the formula for capacitance. IC equal to square root of C by L Vs minus Vc naught sin omega t. So here the capacitor is isolated with the source. There is no connection with the source. So Vs equal to 0. But the initial voltage, the at current state, the initial voltage across the capacitor is it charges to Vs. So this one is Vs. This is the initial voltage at present state. At present state, there is no connection between source. So source voltage is 0. But already stored energy in the capacitor is Vs. So the formula for capacitor current is square root of C by L. This one is minus because Vc naught value is Vs sin omega t. This value is taken as maximum value. So at present state, the current is negative current. So negative half cycle. So they draw the curve for capacitor current. So this one is capacitor current. So take this line as reference line because our aim is to turn off already conducting SCR. Our aim is to turn off already conducting SCR. This SCR is already on state. So we need here our requirement is to turn off this SCR. So to turn off this SCR, we need to trigger this SCR. So the time at which the thyristor, the commutating thyristor triggered is considered as reference line. So assume this line as reference line. So in this state, both Tm on and Ta off, both SCRs are on. So if we take this one as the reference, this one is 0 and this one is pi. Next. This one is for capacitor current. No, main thyristor current does not change as we triggered auxiliary thyristor because it is completely isolated from main thyristor. So there is no disturbance in main thyristor current. So main thyristor continues same state, same on state. In this period, main thyristor continues same on state because there is no disturbance in the main thyristor current. So load current, coming to load current. Once the SCR turns on, it follows main thyristor current like this. So the same IM and I naught are same in this time period because I naught equal to IM. Once the SCR is turns on, I naught equal to IM. So this is I naught and this is IM already completed. Coming to auxiliary current. So up to this point, there is no starting current of auxiliary thyristor. Once the auxiliary thyristor is turned on, it follows capacitor current. It follows capacitor current. So here is the direction of capacitor. For capacitor, it discharges and current flows in reverse direction comparing with previous state. This one is the original state. In this state, current flows in positive to negative. But in this state, current flows in right to left. In this state, current flows from right to left. So that's why I take negative polarities. But for auxiliary thyristors, it allows only unidirectional current. It does not allow bidirectional current. If you take this point is the reference, this one. So the direction of current is like this. It is forward direction. So for auxiliary thyristor current, it is taken as positive half cycle. Actually, it is negative half cycle, but if you consider only auxiliary thyristor, the direction of current is positive like this because current flows in this direction for auxiliary thyristor. It will be reverse for capacitor only, and the capacitor current is taken reverse because of its previous state current is from left to right. Previous state current is from left to right. Comparing with previous state, the present state current is reversed. So the capacitor current is taken as negative. But for auxiliary thyristor, the current flows in forward direction and the thyristor always allows unidirectional current and it will be positive. This one is the auxiliary thyristor current. So here capacitor current becomes zero after omega t equal to 0. So auxiliary thyristor current also becomes 0. This is the one more intermediate state in between 0 to this one is 90 degrees. So at this point, capacitor voltage is Vs. Once the capacitor starts, here the current flows due to discharging of capacitor. Once the capacitor starts discharging, voltage across capacitor also decreases like this. Voltage across capacitor decreases like this. And up to this point, main thyristor current is as usual. There is no change in main thyristor current. This one is load. This one is auxiliary thyristor. This one is capacitor. This one is inductor. Here, if capacitor starts discharging, inductor starts charging. Capacitor discharges and inductor charges. Capacitor discharges from 0 to 90 degrees. So This is for discharging of capacitor and charging of inductor from 0 to 90 degrees. Next, so here capacitor voltage becomes 0 at 90 degrees. At 90 degrees, capacitor voltage becomes 0 because voltage across the formula for voltage across capacitor is VC equal to VC equal to 1 by C integral I dt. This one is the formula for voltage across capacitor. Here IFT equal to sin IFT is the function of sin omega t. So integration of sin omega t is cos omega t. So cos omega t at 90 degrees, cos 90 value 0. So capacitor voltage is 0. So at this point, capacitor voltage is 0. Next, from this 90 degrees to this one is pi by 2, this one is pi. From 90 degrees to 90 less than omega t less than 180 degrees. So once the capacitor completely discharges, inductor starts charging. This one is the charging condition of the inductor. Uh, Up to 90 degrees, capacitor completely discharges and there is no voltage across the capacitor. At that point, voltage across capacitor becomes 0. Now inductor starts discharging. From 90 degrees to 180 degrees, inductor discharging and capacitor charge starts charging. So during discharging, during charging, the polarities are like this. This one is the voltage polarities of inductor during charging. During discharging, the polarities are like this. This one is minus and this one is plus and this one is the direction of current. So here inductor starts discharging and capacitor charges in this direction. Here capacitor starts charging. So the polarities across capacitor is like this. This one is minus, this one is plus because current flows in this direction and capacitor in this time period is charging. In between 0 to 90 degrees, capacitor is discharging. So the polarities are like this plus minus. But in this time period, capacitor is charging. Before 0 to 90 degrees, it is discharging and 90 to 180 degrees, it is charging. So it is charging means the polarities of capacitor is like this. This one is minus, this one is plus. This one is minus, this one is plus. In previous state, voltage across capacitor is taken as plus Vs. In between 0 to 90 degrees, the voltage across capacitor is taken as plus Vs. In between 90 degrees to 180 degrees, voltage across capacitor is taken as minus Vs. So from 90 degrees to 180 degrees, voltage across capacitor is minus Vs. So here capacitor charges gradually like this. Charges up to a maximum value Vs. So this is the voltage across capacitor. This is the voltage across capacitor, which is negative voltage. Which is negative voltage. This one is negative voltage Vs. Coming to circuit. Main thyristor still on state. This one is auxiliary thyristor. This one is the capacitor. This one is the inductor, and voltage across capacitor is like this. This one is minus, this one is plus, and this one is diode. And this one is source. This one is load. So in this condition, 90 degrees to 180 degrees, capacitor charges to maximum negative voltage, charges to maximum negative voltage. So voltage across capacitor is minus Vs, minus Vs. Here minus voltage, same voltage is appear across auxiliary thyristor. This one is auxiliary thyristor. So same voltage is appear across auxiliary thyristor. So same voltage TA is appear across the auxiliary thyristor. So it will goes to reverse blocking mode, because negative voltage appears across thyristor TA. So it will be turned off. So here TA is turned on to turn off main thyristor, but it will take certain time before turn on of TM, before turn off of TM, TA turn off. So once the TA turn off, current becomes zero like this. And this one is the negative voltage. And here capacitor in this case starts again discharging. In this case, capacitor again starts discharging like this. So if capacitor starts discharging, the current here it is open circuited because it will be turned off. This one is negative voltage appears across auxiliary thyristor. So it is in turn off state. So it acts as open circuit. But the discharging current of capacitor flows like this. This one is the discharging current of capacitor. And capacitor does not discharge suddenly. It takes it discharge gradually. So the current also increases gradually like this. And this one is the main thyristor. So here, this is the direction of current. So if you assume the main thyristor constant current is 5 amperes, as capacitor discharges current gradually, the capacitor current also increases from 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 4, 2 to 3, 3 to 4, 4 to 5. Suppose if you assume holding current is 2 amperes, if you assume holding current is 2 amperes, at this time, so maximum current flows in the circuit. This one is IM. So once the capacitor current reaches to 2 amperes, net current becomes 5 minus 2, 3 amperes. 5 minus 2, 3 amperes, which is greater than holding current. So it will be in on state. Next, once the capacitor current reaches, because capacitor current increases gradually, 3 amperes, 5 minus 3, 2 amperes. So still in on state because both currents are equal. Once the capacitor current reaches 4 amperes, 5 minus 4, 1. Here net current is less than holding current. So SCR will be, main thyristor will be turned off. So at this point, capacitor discharges. So capacitor discharging means there is a flow of capacitor current. There is flow of capacitor current like this. So if capacitor starts flowing like this, here auxiliary thyristor is turn off. So it will be the current, auxiliary current is 0 like this. Capacitor current flows through diode. This one is through diode. So once capacitor starts discharging in this mode, main current decreases like this. Main current decreases like this. but load current does not decrease because in this time period capacitor supplies the current to the load. So after certain time gate current becomes 0. This one is the capacitor current. So this is the here in this time period, at this point TM is on. So I draw another line. At this line, TM is on, TM on, TA off because anode current becomes 0. TM on, TA on for this red line. For this blue line at this line time period, TM also off. TM off. TM off. TA already off. Both SERs are off. So both SERs are off. So in this case, capacitor is completely discharges. Capacitor supplies the current, and again capacitor starts charging, and again capacitor starts charging. So here at that point it is turn off. Once the capacitor reaches the maximum current, it acts as turn off. It is turned off. So it is open circuited, and capacitor again starts charging. So the capacitor voltages increases. This is the load current. So capacitor charges to rated voltage. Once the capacitor reaches rated voltage, it acts as open circuit and there is no flow of any current at the load. So the state is similar to previous state. Here, this one is the original first state. We draw the current. This current is due to charging of capacitor. So same current flows certain time. This one is load current. So once the capacitor reaches to maximum voltage, this one is capacitor voltage. Maximum voltage means Vs. This one is Vs. Once the capacitor reaches maximum voltage, it will not charge further because this one is the maximum voltage. So it acts as open circuit. So voltage across the capacitor is constant like this. So same state. Here is also constant. Here also constant. And capacitor current becomes 0 once it reaches to Vs. Here it reaches at this point Vs. At this point, so once the capacitor charges to rated voltage, the capacitor current becomes again 0. Capacitor current becomes 0. This one is this one, and the anode current, main thyristor current is also 0, and load current becomes 0 at this point. So there is no current flow at this point, after this point. So the main thyristor is turned off at this point. Auxiliary thyristor is turned off at this point. So here this total time interval is divided into 3 modes. This duration, this auxiliary thyristor turn on time duration is mode 1. This one is mode 1. This one is auxiliary thyristor turn on time. So after end of mode 1, auxiliary thyristor will be turned off. So next, at this time period, main thyristor will be turned off. This is mode 2. From this point to, from this time to, from this time. This one is mode 2. And this time interval is considered as T2. This one is T2. And this one is T3. This one is mode 3. In mode 3, there is no load current and no thyristor current. And the thyristor will be main thyristor will be turned off at the end of second mode. At the end of first mode, auxiliary thyristor will be turned off, and at the end of second mode, main thyristor will be turned off, and at the end of third mode, there is no flow of current in the circuit. So like this, we can stop the conduction of main thyristor by using competing elements. So here we have two types of times. Suppose if you take normal SCR, this SCR is supplied by sine wave. This one is sine wave. This one is negative half cycle. This one is negative half cycle. So we will start from negative half cycle. This one is minus 5. This one is 0. This one is 5. This one is 2 pi. So minus 5 to 0, and we apply gate signal at this time. This one is the alpha firing angle. So from minus 5 to 0. Minus 5 to 0. SCR will be in reverse blocking mode. If it is in reverse blocking mode, it acts as off switch. Next, from 0 to alpha. SCR is in forward blocking mode. SCR is in half state. Next, alpha to pi. Alpha to pi. Forward conduction mode. Forward conduction mode means SCR acts as on switch. So here the timing of the device is divided into two time periods. So here this time period minus 5 to 0 time period is defined as circuit turn off time. Circuit turn off time. Here from minus 5 to alpha. This total time period is the time for which a power semiconductor device is in off state is known as device turn off time. Circuit turn off time means the time for which the device is in reverse blocking mode. The time for which the device is in reverse blocking mode. The reverse blocking mode time is known as circuit turn off time, and the time for which a device is in off state is known as circuit turn off time. Here from minus 5 to alpha. This one is alpha. Minus 5 to alpha. This time is device turn off time. and this time is circuit turn-off time. So circuit turn-off time is defined as the time for which a power semiconductor device will be in reverse blocking mode. That time is defined as circuit turn-off time. So in circuit turn-off time, reverse voltage appears across the device. In diode, device turn-off time, the voltage may be either positive voltage or negative voltage, but the device is in off state. The voltage is either reverse voltage or forward voltage, but the device is in off state. That one is device turn off time. In device turn off time, the device is completely in off state. So complete off time. But circuit turn off time means the time for which the device is in reverse bias condition is defined as circuit turn off time. That is the difference between circuit turn off time and device turn off time. So coming to this waveforms, so this one is the negative voltage. Here, this one is the negative voltage. So here we need to calculate circuit turn off time of auxiliary thyristor. Main thyristor is always in forward blocking mode. It will not in reverse blocking mode, but the time the auxiliary thyristor is in reverse blocking mode. This one is in reverse blocking mode. So reverse blocking mode means the time for which the device is in reverse blocking mode means negative voltage across the device. So here, if you take the voltage across the capacitor, voltage across capacitor is nothing but voltage across auxiliary thyristor. In this mode, this one is negative voltage, this one is positive voltage. This curve represents positive voltage, so there is no problem of calculating circuit turn off time in this time period. In this time period, the device is in conduction state. So 0 to 90 degrees, the device is in conduction state, and 90 degrees to 180 degrees also, the device is in conduction state like this. Here is the gate current. This one is the auxiliary thyristor current. Here it will be turn off at this point. It is turned off at this point. So this voltage is reverse voltage. This voltage is reverse voltage. After this point, the voltage is positive. So we no need to consider circuit turn off time in this time period. We need to consider circuit turn off time only in this time period, because in this time period only the device is in off state and negative voltage across the device. So we need to calculate this time period. This time period is here mode 1 and after T1. So after pi 1, and this mode is taken as mode 2, and this time is taken as T2. So in this mode, voltage across capacitor. Now the formula for voltage across capacitor. Vc equal to Vs minus Vc naught cos omega t plus Vc naught cos omega t. So in this time period, there is no voltage. Vs is 0. And Vc naught means Vs. Vc equal to minus Vs cos omega t plus. So this one is also voltage across capacitors. Capacitor charges to a maximum voltage of Vs. So this one is negative voltage, okay, which is minus Vs. Is minus Vs. Here capacitor current IC equal to root of C by L Vs sin omega t. Is equal to 1 by integral of C into I dt. This into integral of C by L into this one is Vs, this one is sin omega t. So sin omega t becomes cos omega t, cos omega t by. So here CC gets cancelled. So 1 by square root of LC Vs cos omega t. This one is Vs, this one is C by 2 omega, and this one is minus, because integration of sin omega t is minus cos omega t by omega. Omega means 1 by square root of LC. So omega, this value cancel. So Vc equal to minus Vs cos omega t. So at the end of mode 2, at the end of this one is pi, this one is T2. At the end of mode 2, the voltage across capacitor is equal to thyristor voltage, which is negative voltage, which is taken as reverse voltage. This one is reverse voltage, and in this time period minus cos of omega t means pi plus T2, pi plus T2. So cos pi plus T2 means minus cos T2 minus cos T2. This one, sorry, this one is omega T2. So Vs cos omega T2. At this time, at the end of the mode 2, voltage across the auxiliary resistor, this this one is VR. Now we need to calculate T2. This one is the reverse voltage. So to calculate T2, the current in capacitor I naught equal to Im sin omega t sin omega t2. This one is sin omega t2. This one is reverse voltage and this one is sin omega t2. So here I naught by Im equal to sin omega 2t omega t2. So omega t2 equal to this one is omega t2 equal to sin inverse of I naught by Im. So t2 equal to 1 by omega sin inverse of 1 by omega sin inverse of I naught by Im. So like this, by substituting this formula here, omega equal to square root of LC. So it means square root of LC into sin inverse I naught by Im. By substituting these values, we can calculate T2, and by substituting these values in this equation, we calculate reverse voltage, across the plates. But our aim is to calculate circuit turn-off time. So voltage across capacitor VR equal to this one is 1 by C IDT, and this one is from 0 to here the negative voltage appears from 0 to TT. Into integration of IDT with respect to TT means T. If you apply limits, then this one is T2. This one is not T2. So this one is circuit turn-off time TCF. Circuit turn-off time. So this time period only the voltage across the auxiliary resistor is negative voltage. So ITC. ITC. So circuit turn-off time TC equal to VR. VR into C by here the current is I naught. So this one is the formula for circuit turn-off time. This one is the formula for circuit turn-off time. Once again, I repeat the computation process of main thyristor. So this is the main thyristor. To turn off the device, to turn off main thyristor, we need to trigger TA. So before triggering TA, there is some flow of current through this capacitor. Through this capacitor, there is some flow of current. That current is I0 and which is supplied up to charging of the capacitor. Once the capacitor charges, it acts as a open circuit. So this is the waveform. After open circuiting, current becomes 0. So once the thyristor is turned on, main thyristor current increases like this, and already there is voltage across capacitor, and current flowing in the capacitor is 0 until triggering next device. So in this time period, current flowing in the capacitor is 0. Once the main thyristor is turned on, once the auxiliary thyristor is turned on, capacitor starts discharging. So if it is turned on, capacitor starts discharging, and again after certain time capacitor charges, and again discharges like this, and current flows in this direction, and main thyristor will be turned off. So like this we can turn off main thyristor by triggering auxiliary thyristor. This is class B commutation. Any doubts? Any doubts about class B commutation? Okay, next class C commutation. So in class C, the other name of class C commutation is complementary commutation. So in this commutation, at a time, one device will be turned on and other device will be turned off. That's why it is also known as complementary commutation. So in this mode, current will be continuously flowing in this circuit, and there is no disconnection of load current. The load current is continuous, but the devices will be turned off. So this one is the circuit diagram. Vs. This one is resistance R1. This one is resistance R2. And capacitor is connected in between two resistors like this. And this one is one thyristor. This one is T1. And this one is T2. So for classic commutation, we assume that initially T2 will be in on state. If the T2 will be in off state, The direction of current is initial state. This one is Vs. Once the capacitor charges to maximum value, it acts as open circuit. This one is R2. So initially, we assume that voltage across the capacitor is Vs. This one is R1. And here T1 is off state. T1 is on state. This one is the T1. Current flows in this direction. So we assume that capacitor is initially charged to source voltage. So before turn on of T2, the voltage across the capacitor is like this. Once the SCR is turned on, already once the SCR is turned on, before this state, the polarities of capacitor is like this. So once T2 is turned on, the current flows in this direction. So here voltage across capacitor changes from minus Vs to 0, and again 0 to Vs. It changes from minus Vs to 0 and again from 0 to Vs. If it reaches Vs, it acts as open circuit. So during discharging, the polarities of capacitor is like this. And the direction of current is like this. After completely discharging capacitor, capacitor starts charging, and the direction of current is like this, and the polarities across capacitor is like this. So at the end of the current flows in this direction and capacitor starts to maximum voltage and it acts as a open circuit. So in present state, the voltage across the capacitor Vs and the polarities are like this. This one is plus and this one is minus. So initially we assume that T2 is turned on. So before turn on T2, there is flow of current and the voltage across if there is no voltage across the capacitor. Assume initially there is no voltage across the capacitor. Tell you again. This one is the circuit. This one is R1 resistance and this one is R2 resistance. This one is main thyristor. Both are main thyristor. This one is T1. This one is T2. This one is T2. This one is capacitor. So if you take the T2, if the gate signal is applied T2, initially both the thyristors are in off state. in off state, then there is no flow of current in the circuit. Initially, both the thyristors are in off state, so there is no flow of current in the thyristors. So once the thyristor T2 is triggered, if there is no voltage across the capacitor, if you assume there is no voltage across the capacitor, once the capacitor is triggered, once the T2 is triggered, the current starts flowing like this, and some of the current starts flowing like this. And capacitor charges to, this one is plus and this one minus. Capacitor charges to up to its rated voltage Vs. This one is Vs, this one is Vs, and it reaches to rated voltage Vs. Once it reaches rated voltage, there is no flow of current in this path. There is no flow of current in this path. Before reaching Vs, the total thyristor current is I22 equal to, this one is IT2. IT2 equal to IR1. This one is IR1 current. This one is IR2 current. This one is IR1. This one is IR2. So before charging Vs, total thyristor current IR2 equal to IR1 plus IR2. So once the capacitor charges to rated voltage, this current becomes zero. This current becomes zero, and total thyristor current equal to only IR2. So once the polarities of the capacitor is like this. This one is plus, this one is minus, and this one is the main thyristor current is, this one is T2, and IT2 current flow in the circuit. This is the initial conditions. So once if you trigger T1, we will see the status of the circuit. This one is R1. This one is R2. This one is R2. This one is capacitor. And voltage across capacitor is like this. This one is plus, this one is minus, and this one is Vs. And this one is T2 thyristors. If you trigger this one, this acts as short circuit. This one is yes. Before triggering T1, T2 is also in on state. Before triggering T1, T2 is in on state. This one is the on state of the T2. Once we trigger T1, T1, it acts as short circuit. This one is the short circuit. So if it is short circuit, if you bring this point to this side, if we bring this plus to this point, it means here anode voltage is negative, cathode voltage is positive. So it means negative voltage appears across T2. So T2 will be turned off. So T2 will be turned off once we trigger T1. Before triggering T1, there is no problem because there is no connection in between these 2 points. In between these 2 points, there is no connection before triggering T1. Once we triggering T1, it acts as a short circuit, and this terminal, both the terminal are maintained at same voltage. So if it is positive voltage, here the cathode voltage is also positive. So negative voltage appears across T2. So T2 will be turned off. So T2 is turned off. Now we observe the behavior of capacitor in this state. So here capacitor current flows in this direction because the capacitor polarities is like this, plus minus. So here capacitor current is divided into two parts. One is during discharging and another one is during charging. So here capacitor starts discharging. This one is main current is supplied by through R1. So up to a particular time period, the current equal to current in first thyristor IT1 equal to IR1 plus IR2. Here IR2 current is divided into two parts because during discharging there will be some flow of current, and here voltage across the capacitor changes from this one is if you take only for capacitor, this one is minus Vs. So minus Vs to 0. So during this time period there will be some flow of current. Again after reaching 0, it again starts charging. So 0 to Vs. Now the polarities across the capacitors, this one minus, this one plus, this one minus, this one plus. Once the capacitor reaches to rated voltage Vs, it acts as open circuit and current flows in the main thyristor only in this path, only through R1 resistor, and there is no current flow because it acts as a open circuit. Next, if you want to turn off this thyristor, again turn on this thyristor. This thyristor is in conduction state. This one is main T1 thyristor. This thyristor is in conduction state, and this one is R1 resistor, and this one is capacitor, which acts as open circuit, and the polarities of voltage is like this, minus plus, and the polarities of voltage is minus plus. This is R2. This is R2. This is T2. This is T2. So present T1 is conducting. Present T1 is conducting, and T2 is in off state. Once we trigger T2, if T2 is triggered, the capacitor starts discharging. The capacitor starts discharging, and it acts as a short circuit. If it acts as a short circuit, the voltage at this point and voltage at this point is same. So here Anode voltage is negative and cathode voltage is positive. So negative voltage appears across T1. So T1 will be off state and T1 is on state. Again, in this state, capacitor discharges completely to zero. Capacitor discharges completely to zero from minus Vs to 0. So again, from 0 to Vs it charges. So again, from 0 to Vs it charges. Now in this case, the polarities of capacitor is like this. This one is plus and this one is minus. This voltage is reverse voltage for T2. So here this voltage is appear due to turn on of T2, and once the next device is turned on, same voltage until application of until triggering next thyristor, there is no effect of this voltage. There is no effect until triggering T1. If T1 is triggered, this negative voltage appears across T2 because it acts as a short circuit. If it is not triggered, this voltage is not appear across T2. So T2 will be in conduction state. So any doubts regarding this T1 and T2? Here, this type of computation is now known as complementary computation because once T1 is in turn on state, other device will be in turn off state. If T2 is in turn on state, T1 is in off state. Hello? హలో
చెప్పండి సార్.
అంటే క్లాస్ అర్థమైందమ్మా ఏమైనా డౌట్స్ ఉన్నాయా
అర్థమైంది సార్.
అర్థమైందా హలో హలో ఎనీవన్ ప్లీజ్ రెస్పాండ్
అర్థమైంది సార్.
ఓకే అండి ఓకే
ఓకే సార్.
సార్
So these are the waveforms. This is the classic computation and these are the waveforms. So we'll start from this point. Initially, we assume that voltage across capacitor is this one is waveform of capacitor. Initially, if T2 is triggered, negative voltage appears across the capacitor like this. This one is minus V1, minus Vs. So at this time period, gate pulse is applied to main thyristor T1. So if gate pulse is applied to this thyristor, the voltage across the thyristor VT1, voltage across the thyristor becomes 0, and this one is current flowing through main thyristor. This current is a combination of T2 current and T1 current. This is the combination of R1 current and R2 current. And it is divided into again two parts during charging and during discharging of the capacitor. This one is the discharging current and this one is the charging current. Once the capacitor reaches to maximum value means once the capacitor voltage, this one is the capacitor voltage. So this one is discharging. This one is discharging. Here the initial voltage is minus Vs. The initial voltage is minus Vs. The capacitor voltage changes from minus Vs to 0. This one is discharging of capacitor, and again it reaches from 0 to plus Vs. Once it reaches plus Vs, it will be constant. And this one is voltage across the inductor. So same voltage appears across thyristor T2. So after this line, this is the current due to single resistance. So in this mode, T1 is turned on and T2 is turned off. So once T1 is triggered, once T2 is triggered, at this one is the triggering of second thyristor. Once it is triggered, the voltage across the capacitor gradually decreases like this. It means it discharges, and again from this point to this point it charges, and there is a negative voltage appears across the SER until turn on of same SER. So this one is the negative voltage which is appears across T1. So if you draw the capacitor currents, if you draw capacitor current, the capacitor current is present only during capacitor charging and capacitor discharging. This one is capacitor discharging, and this one is during capacitor charging. So like this, these waveforms present at a particular time. So once the thyristor is in completely conduction state, there is no flow of capacitor current. So these are the waveforms related to class C commutation. So if you have any doubts, ask me.
సార్ మెటీరియల్ ఎప్పుడు ఇస్తారు సార్?
మెటీరియల్ ఫస్ట్ యూనిట్ అంతా కంప్లీట్ గా ఇస్తానమ్మా. సెకండ్ యూనిట్ నుంచి టాపిక్ వైజ్ ఇస్తాను. ఈ యూనిట్ కంప్లీట్ అవ్వగానే ఇస్తాను.
అంటే ఇప్పటి వరకు చెప్పిన దానికన్నా ఇవ్వచ్చు కదా సార్?
ఇప్పుడు వరకు అంటే అది ఎడిటింగ్ కొంచెం ప్రాసెస్ టైం పడుతుందమ్మా ఎడిటింగ్ చేయడానికి. సాఫ్ట్ కాపీ ప్రిపేర్ చేయాలి కదా, అంటే ఆల్రెడీ ప్రిపేర్ చేసింది ఏం లేదు, మీకు ఫ్రెష్గా ప్రిపేర్ చేయాలి సాఫ్ట్ కాపీ.
సరే సార్.
సో అందుకని ఇప్పుడు టైం పడుతుందండి. నెక్స్ట్ సెకండ్ యూనిట్ నుంచి టాపిక్ వైజ్ ఇచ్చేస్తాను.
సరే సార్.